And okay, so wait, everything is fine. I'm sharing screen, video is on. Yeah, okay, good. So no class on Monday. And let me remind you where we were on Wednesday. On Wednesday. So I was mentioning the fundamental theorem of finite type invariance, which is sort of reduction of finite type invariance to combinatorics, to finite combinatorics. I mean, for each specific degree, it's finite. The overall problem is not finite. And it's called the fundamental theorem of finite type invariance. In a minute I'll mention why. It's first due to Kontsiewicz, but by now there are several other proofs by various other people. So it says every weight system which satisfies the framing independence and the four-term relation, so every W which is an element of the space I will now declare to be calligraphic W sub M, which is the dual space of chord diagrams with M chords modulo the framing independence relation and the 4T relation. So for every such W, there exists an invariant V of type M, so V in Vm, such that W is the weight system is the top derivative of that invariant, right? It's roughly the mth derivative of that invariant. So first of all, why the fundamental theorem? Well, it's fundamental, okay? It's the fundamental theorem of the subject. It means you've reduced the problem of finite type invariance to combinatorics. But also, it's kind of like calculus, right? So basically, W is the mth derivative of an invariant. And we're saying every derivative can be integrated to an invariant, okay? So hence the name. Now, a few definitions, or a little bit of a couple of definitions. So this space here is useful and happens a lot. So, and we need it a lot. So I will call it A, calligraphic A, sub M, M for the degree, and up R, R for reduced. And the reason it is reduced is because there is also an unreduced version, and the unreduced version is A sub M without the R, and it is defined to be the M chord diagrams modulo only the 4T relation. Okay, sorry, notice the bracket here is enclosing the space, not the dual, not the star. The thing inside the parenthesis is what I call AM reduced. So, the dual of AMR is finite type invariance of type M modulo type M minus 1, okay? And the dual of AM is same thing but for framed knots, because the framing independence relation was relevant only for unframed knots, okay? And then I mentioned that the problem is reduced to combinatorics, or at least for each finite M, the problem is reduced to combinatorics. So here for your entertainment is the result of explicit computations. So basically, if you want to figure out what is A7, all you have to do is to draw all chord diagrams with 7 chords, and then draw all 4 term relations, and basically find the dimension of the span of the 4 term relations and subtract it from the overall dimension, and that's so basically it's a problem in linear algebra. So you punch it into the computer, you get the computer to solve linear algebra problem, and the result is that as M goes from 0 to 12, that's as far as we know, the dimension of AM is 1, 1, 2, 3, 6, 10, 19, 33, 60, 104, and so on. And the truth is, this was computed more than 20 years ago. So I'm pretty sure you could go a few dimensions beyond by now, a few degrees beyond by now, but nobody bothers because there's not much to do with just the numbers. Okay? So again, the moral of the story is, if you want to know how many finite type invariants are there of type 12 of framed knots, there are 548 plus the ones of degree, plus all the ones that are already of type 11. So 548 plus 313 plus 184 plus 104. So basically the sum of all of these numbers. There's quite a few. Quite a large number. Okay? Good. So the next definition, so people who just came, I just want to remind you, no class on Monday. Don't come. Good. So the next definition is, so you know, kind of like Chobanov homology, kind of like other places, when you have space, one space for each dimension, or for each degree, for each m, it makes sense to pack them together. Okay? So let's pack them together. So let A, so A without a subscript, be the direct sum as m goes from 0 to infinity of A sub m. Similarly with R, so you know, I'll put the R in parentheses, and by that I mean either with R or without R. Okay? And just to be clear, so the direct sum is, infinite direct sum in common conventions mean like a sequence of elements, one belonging to each space, but a finite such sequence, or a sequence that becomes zero after a point, after a while. Okay? So, okay? But there is also the infinite product. So the infinite product, so let's call it A hat, again, maybe with R, maybe without R. So A hat is defined to be the infinite product as m goes from 0 to infinity of A m, maybe with R, maybe without R. And the infinite product just means infinite sequences, A0, A1, A2, where each AI is in the corresponding calligraphic AI. Okay? So this is infinite sequences, and these are finite sequences. In practice, this space is much more useful, and often I will forget to put the hat, but will mean it anyway. Okay? Good. Now, so what about these spaces? So, okay, the dual of AM is finite type invariance, is invariance of type M. So, or more or less. Okay, so I'm being very, very loose now. So, the dual, the dual of AM is roughly invariance of type M. So the dual of A is roughly invariance of all types. So basically all finite type invariants. Now, this is the dual. Okay? But the invariants are functions on knots. So roughly speaking, invariants are the dual space of knots. So this is completely loose, okay, completely informal. But the point I want to make is that A and K are kind of brothers, sisters, I don't know, cousins. They're both duals of the same thing, okay? In slightly different senses, okay? So you somehow can expect that whatever structure there is on K, there will be similar structure on A. And that's what I want to do. That's the point of today's class. So what structure is there on K? So K, I'm not sure if I ever said what K is. So K is simply the set of all knots. Okay? So what structure is there on K? So K has a commutative product. So if there are two knots, there is a way to multiply them. So why? Okay, so first of all, K has two versions. There is the knottings of a circle, which is what we've always talked about. Okay? And there is the knottings of a long line. So I'm introducing notation without defining it, but each time I introduce a notation, it's really a definition. Okay? So what is a knotting of a long line? A knotting of a long line is when you have a line starting at minus infinity. So it starts straight at minus infinity, it ends straight at plus infinity, and in between it does some knottingness. I mean, the knot I wrote is trivial, but you get the point. Okay? So these two things are in fact the same, or more precisely, isomorphic. Why are they the same? Because, well, if you have a long, so such a thing, by the way, is called a long knot. So if you have a long knot, you can just take the two ends and connect them. Okay, you just add a line connecting the one end to the other end. I mean, strictly speaking, the end is at infinity, so you take a line from near infinity to near infinity at the other end and connect the two ends. Alternatively, if you have a circular knot, so if you have a round knot like this, you can pick a point, cut it open, and pull to infinity on both sides. And it's easy to check that the result is independent of which point you picked. Okay? Now, the space K of a line, so the space of long knots, clearly has a product. So this space clearly has a product. So if you have two long knots, so if you have K1 and it's a long knot, and if you have K2 and it's a long knot, you just define their connected sum, the product called the connected sum, to be, well, you simply put one after the other along a long string. Okay? This product is commutative. So, I mean, so far everything was obvious, But the fact that it's commutative is actually not entirely obvious, but it's kind of cool. Okay? So suppose I wanted to show that this is equal to whatever you do, whatever you get, sorry, I wanted to show that this is equal to the same thing, but with K2 coming first and K1 coming second. And remember that the lines are oriented, so it's not, you know, it's not just. What do you do? Any ideas?
Can you sort of pull K1, make it small, and then pull it around?
Yeah. So basically, you shrink K1 until it looks like, you know, a tiny bug, fly, whatever. So you shrink K1 and then you slide it. So, you know, so you shrink K1 until it is so small it looks like a tiny thing. Then you slide it through K2 until it comes out on the other side. And then you expand it back again and you got this thing. Okay? So this is clearly a commutative algebra. Sorry, not algebra. A set with a commutative product. Good. Now, K-dual, so the dual space of K, the space of not invariance, at least if you take values in a ring, also has a product. So this is also a commutative algebra, because if you have two invariants, you can multiply them. Furthermore, at least intuitively, well, we really looked at polynomial invariants, okay? And our intuition from polynomials on Rn says that if you take two polynomials in Rn and you multiply them, again you get a polynomial in Rn. So we expect that even if we restrict our attention to finite type invariants, the product of two such invariants will be again finite type. We haven't shown it yet, but we can expect it. Okay? So, K is roughly an algebra. K-dual is an algebra. And we've already talked about vector spaces that are both algebras and their dual are algebras. So they're both algebras and co-algebras. And such vector spaces are called, well, if they also have some property about the inverse, are called Hopf algebras. But if they don't have this property about the inverses, and I don't want to get into inverses at the moment, they're called bialgebras. Okay, so this is the next theorem. So theorem. Oh, sorry, I'm out of pages. Append page. Let's append a few and continue. Sorry about that. So theorem. So again, the inspiration comes from K, but I'm going to make the statement about A. So the space of chord diagrams modulo 4-term relations, and I didn't put R because I didn't feel like it, so I don't mod out by framing independence relation. But the same is true if you do mod out by framing independence relation. So this A is a connected, graded, commutative, and co-commutative bialgebra. So let me explain each of the words. First of all, graded is the same meaning as when we talked about Chobanov homology, even though the context is completely different. So graded is simply the fact that the space A is an infinite direct sum of spaces, and we just call them the degree m pieces of A. Okay, that's nothing. Connected, so connected is a word that comes from a completely different place. So if you know anything about homology, so homology is the homology of a topological space is graded because every homology class has a dimension, right? There is zeroth homology, first homology, second homology. All the degrees are non-negative. There's no -1 homology. And the topological space is connected if and only if its H0 is one-dimensional. Okay? So the word connected, when spoken about graded graded vector spaces, was borrowed and simply stands for all the m's are greater than 0 and the dimension of A0 is equal to 1. In our case, why is the dimension of A0 equal to 1? Well, A0 is the space of chord diagrams with 0 chords. There is only one. The empty chord diagram, no chords, and no relations. So it's a one-dimensional space. Okay, so this is completely trivial. I mean, the connected and graded are just empty statements, but it's good to put them. Okay. Now, what does commutative and co-commutative means? So commutative means that there is a map M from A tensor A into A, which satisfies the associativity. So we already talked about it, I'll mention it once again. So if you go from A tensor A into A in two ways, so you go first to A tensor A via M tensor 1 and then via M, or you go to A tensor A via 1 tensor M and then via M, then this diagram commutes. That's the fact that the product is associative. And second, that product is commutative. I'm asserting it is commutative. So this means that if you go from A tensor A to itself via the map that transposes the two factors, the transposition, or and then you go to A using the multiplications, and this diagram commutes. Okay, so that's the commutative algebra bit, and now the co-algebra bit. So there should be a map delta from A to A tensor A, such that the reverse diagrams hold, are satisfied. So A goes to A tensor A goes to A tensor A tensor A, or, sorry, by delta and then delta tensor 1 is the same as going from A to A tensor A, going to A tensor A tensor A via delta and 1 tensor delta, and also a diagram which I will not write for co-commutativity. And finally, there is some compatibility between sorry, I misspelled, but it doesn't matter. There is some compatibility between M and delta, and I think I mentioned it when we talked about Hopf algebras before. So I want the coproduct to be a morphism of algebras this is an algebra, this is an algebra, so I want the coproduct to be a morphism of algebras, and when we get to it, we will talk about what it means. Okay, it's actually completely trivial. Okay? Anyway, well, let's start showing that these things exist. Okay? Right, so far I'm only asserting. I didn't tell you what is M, I didn't tell you what is delta. So first of all, let's imitate from the world of knots. Right, in the world of knots we had that K of a circle is isomorphic to K of a line. And I want to assert the same for A. So theorem A, well, so far we didn't say A of a circle, but now to emphasize, let me call it A of a circle. So these are chord diagrams whose skeleton, whose the thing other than the chords is a circle. Okay? And I'm asserting that it's isomorphic to A of a line, where what is A of a line? So it's linear combination, so it's chord diagrams whose skeleton is a line. So it's linear combinations of chord diagrams where the chords, instead of running inside a circle, they run atop a line. Modulo the same relations, the framing independence relation and the 4T relations. And just to be clear, let me tell you what they are. So what is the framing independence? Sorry, not framing independence, not framing independence. I didn't put the little r. Okay? The little r means reduced, meaning, but sorry, I'm not imposing the framing independence relation here. So I'm not imposing it, but since I mention it, I may as well say that it makes sense in the contents of long chord diagrams just as well. Namely, a chord diagram that has in it a small chord is so a chord which is not intersected by anything else, so all the other chords so nothing comes between the two ends of this small chord. So the framing independence relation says that this is equal to 0. Anyway, we're not using it, we're using the 4T relation. So let me remind you what is the 4T relation. So the 4T relation says that, okay, here is 4T, that if you make 4 chord diagrams by, well, all 4 chord diagrams have the same chord in the same place. All 4 diagrams have an additional chord which begins in the same place in all cases, and that extra chords can end either before the beginning of this chord or after its end, or after the beginning of that chord, or like that, or like that. And in addition, there may be further chords that have to be the same in all four pictures. So maybe there will be a chord going from the middle of this arc to the middle of that arc in all cases. Okay, good. So I still have to prove the theorem. Okay, so proof. So one map is obvious. It's obvious that you can map this to this. Namely, if you have a chord diagram on a line, you can close the line to make a circle. So this one is obvious. And it's also obvious that the relations become relations. So I mean, it's well defined even when you descend to the quotients. Okay? The other map is less obvious. So suppose you have a chord diagram whose skeleton is a circle. I need to show you, well, to go the other way, right? So to go that way, I need to show you that, well, I'm going to cut the circle somewhere. Cut it open and turn it into a long line. But I have to show you that if I cut it here or cut it there, I get the same result. Okay? Now, what's the difference? So the difference is that, so if I view it at the output, so if I view it as a long chord diagram, the difference will be, well, I'm going to have a certain chord diagram, and there will be one particular chord that used to be, so this chord here, that used to be right before the cut point, right, this chord here, goes from being, let's orient things. So this chord here used to be right at the start of the long line, and when the cut moves to here, it becomes right at the end of the long line. So it's one end of chord, that moves from, I missed the colors. So there is one chord that moves from being here to being here. From connecting at the beginning of the line to connecting at the end of the line. I need to show you that this is the same. Okay? But these two chord diagrams are not the same as chord diagrams. I need to show that they are the same in the quotient space, modulo 4t. Okay? Is it clear what I need to show? Good. So, here's how you do it. So, again, I have my chord diagram. It has, I don't have to write it the same way as, so it has this one special chord. I need to show that if I connect it to the left or connect it to the right, I get the same thing. So what I'm going to do is I'm going to connect it in many other places. So I'm going to put a little hook, or two little hooks near the end of each chord. So two little hooks here, 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 basically two little hooks here, two little hooks around the end of each chord in the picture drawn here. And I'm going to put signs on these hooks and I'll alternate the signs. So this one comes with a plus, minus, etc. Okay? And I'm going to consider, I'm going to consider, what should we call it? S. So S will be the sum of all ways of connecting the loose end, so the top, I don't know, what should we call it? The connector, C. So, of all of the ways of connecting C to the hooks with signs. So, in other words, plus connecting it to here, minus connecting it to here, plus connecting it to here, and so on. Okay? and this is an element, so each such connection is a chord diagram. So this is an element of A. Yeah, it's an element of A. So now let me rewrite this sum or rearrange this sum in two ways. Okay? So on the one hand, I can go over all the chords and sum over the four hooks that are next to their ends. Okay? So I can write it as sum over chords of, for each chords, sum for hooks next to its ends. And actually, the way I drew it, there are two exceptional hooks, namely the two hooks near the base of the chord I'm trying to play with. So, so plus two further connections. Okay? But now, if you look at this, okay, the two ways of connecting C to here both give, whether you bend it to the left or bend it to the right, you're going to get a little hump. The same thing, but you get it with two opposite signs because the signs were alternating. So these two contribution gives 0. The sum of, if you fix a chord and you look at the four ways of connecting C to the four hooks around that chord, so for example, these two plus these two, if you look at it, it precisely forms a 40 relation. Okay? So each such sum is a 40 relations, so you get a sum of 40 relations plus nothing. So this is equal to 0 in A, because in A we modded out by 40. Okay? On the other hand, I could group the sum in a different way. I could sum over edges. So if you look at the edges on the base of the long chord diagram, then each edge has, so this edge, 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 and this edge. So each edge has two hooks on it, and they come with opposite signs. Okay? So on the other hand, our 0 here is equal to sum over edges of sum over plus and minus on hooks on each edge. But then there are two exceptional edges, the one at the beginning and the one at the end. So plus contribution from hooks at ends, right? Because these two hooks are not on an edge. Okay, not on an internal edge. Well, this is clearly 0, and we are left with what we wanted. So the two contributions from the two ends, the two ways of connecting C to the left or to the right, add up to 0, which means that, sorry, with opposite signs, so which means that they're equal. Okay? Are you with me? Leonard, you're disagreeing.
Yes, I'm not sure why the second line equals the third. I don't know why you are doing edges.
Oh, I'm saying, look, I have this big sum over all hooks. but I can organize the sum in two ways. So it's not that the second line is equal to the third. Both lines are equal to S. Both lines are equal to the sum over all hooks. So one way of organizing this sum is by summing over chords, and for each chord there are 4 hooks around it, and if you go over all the chords you get all the hooks. Again, with some 2 exceptions. And the other way is to sum over these black edges, and on each black edge there are 2 hooks, and if you sum over the black edges, the hooks on them, you get again all the hooks. So there are 2 ways to present S, or 2 ways to rearrange S, and one way is 0 modulo 4t, the other is mostly 0 except the 2 contributions at the ends, which is what we wanted to show. Okay, good. But now so now I can finally define the algebra structure. So if I want to multiply 2 chord diagrams, so it's completely clear that A of a line has an algebra structure. Namely, if I wanted to multiply this chord diagram with that one, I simply put them side by side. I put them along each other on a long line. Namely, the product is defined to be, you just put them one after the other in a long line. Okay? Now, why is this, sorry, this product is clearly, so this product is clearly associative. And I claim that it's also commutative. So why is it commutative? Well, it's commutative because, in fact, because we've just shown it. Because suppose I wanted to exchange these 2 little creatures, little diagrams, okay? So what I would do is, well, I would close this to a loop. Now that it is a loop, I could slide this one to the other side, and then open it again, and we've just shown that it doesn't matter how we open, we get the same answer. So, okay? So that's one way to see it. Another way to see it, maybe I like it more, but it's a bit, what do you call it? Creepy. Okay? So, you know, these are spiders. We want this spider to climb over that one and come on the other side. So, let it climb foot by foot. So, let this foot climb to the other side. So I want to move it from here to here. And how do I do it? By exactly the same argument. Namely, I put hooks and connect it to various places in the middle, exactly the same argument. And then I move the next foot, so it's kind of so one bug climbs over the other, and at the end they switch sides. Okay, are you with me? So A is an algebra. Good. A commutative, co-commutative algebra. Now, I want to claim that it's also a co-algebra. So, okay. Yeah, you know what? Let me first tell you. Okay, let me first do it. Okay. So let me just do it. So I need two propositions. Okay. So proposition number one is the statement that, so how was it supposed to be a coalgebra? Its coalgebra structure was supposed to reflect the fact that when you multiply invariants, you get an invariant back again. And more strongly, if you multiply two finite type invariants, you get a finite type invariant once again. So this should be my first proposition. So the proposition says that if V1 is a finite type invariant, so it belongs to the space of finite type invariants of type M1, and V2 belongs to the space of finite type invariants of type M2, then their product, V1 times V2, and again, you should be thinking that they're like polynomials. So if you multiply a polynomial of degree M1 with a polynomial of degree M2, the result is a polynomial of degree M1 plus M2. So you're expecting this to belong to Vm1 plus M2. And I assert that this is indeed the case. Okay? And proposition number 2 is, well, how exactly this induces a coproduct. Okay? So I claim that there exists a unique coproduct, and before I use triangle for the coproduct, but this specific coproduct is usually denoted with a box. My apologies. So there exists a unique map delta going from A to A tensor A, which has the property that if you want to compute the weight system of a product, so the weight system of a product of two invariants is equal to, so what is this? The thing written here. The thing written here is a function on chord diagrams with values in the ground ring. Right? If I am to multiply invariants, they should be in a place where I can multiply them. So this is a function from A to the ground ring. Let me produce to you another function from A to the ground ring. So first go from A to A tensor A. So box goes from A to A tensor A. And then compose it with the function that takes A tensor A to the ring tensor the ring by using by using WV1 and WV2. So WV1 tensor WV2, and then simply multiply. So basically, the map here is delta followed by, have I used this notation before? So this means composition done right. So, maybe I'll make a little aside. So, if circle G computed on, or let me say differently. If you have two maps, F and then G, then you write their composition G circle F, and it's annoying because you have to reverse. So one should invent a notation for composition going the right way. So the notation is F / G. This just means F / G means G circle F. But it's much more convenient in many places to use this notation. So you first do the coproduct, and then you do, wrong color, and then you do WV1 and multiply with W of V2. So after the coproduct you have two tensor factors. On the first tensor factor you apply this, on the second one you apply that, and you multiply the results. Okay? We're out of time, which is sort of amazing because there is still a lot to say, but I suppose I'll continue on Wednesday by explaining why these two propositions are true. But the result is sort of, there is actually a rich structure behind finite type invariants. They're structure. It becomes algebra back again. Okay, so see you on Wednesday. Any questions, any comments?
Yeah, can I ask a question from the previous lecture?
Sure.
Okay, about the faulty relations.
Yeah.
If you could explain to me how you got the chord diagram from one of the relations again. I didn't quite understand that.
This is a bigger question. So, I mean, maybe we should declare that the recording is ending, the class has ended, and you should remain, and I'll explain it in private. Okay? And people are welcome to stay, but that's kind of after the end of class.